It's just gone 11 Eastern time, so welcome to another session. Today we're very happy to have Levi Crews, who will present his paper with Tamara Carlton at Berkeley and Ishan Nath at the Harvard Kennedy School on agriculture, trade, and global water use. Just a reminder, if you've got questions throughout the talk, just post them in the chat. I'll gather them and we'll ask them at the end of the talk. So Levi is an assistant professor of economics at UCLA. His research focuses on macroeconomics, spatial economics, and international trade, with a particular focus on how the spatial allocation of economic activity affects macro aggregates and welfare in the long run. Before joining UCLA, he was an IES postdoctoral fellow at Princeton University, and he received his PhD in economics from the University of Chicago in 2023. So Levi, you've got 45 minutes. Take it away.
Awesome. Thank you all for having me. It's going to be a lot of fun to be here. So as Connor said, this is a joint work with Tamara Carlton at UC Berkeley and with Ishan Nath over at Harvard. So what I want to do is start by putting two examples on the table, and the first is going to be almonds in California. So California almond production has nearly doubled over the last 20 years to the point that now California accounts for roughly 80% of global almond production, and 70% of those almonds get exported abroad. But this period of rapid expansion in almond production has coincided with severe droughts and land subsidence in California's Central Valley due to excessive groundwater extraction. And as the headline on the left suggests, we think these two trends are related because almonds are one of the most water intensive crops that we grow. So it takes roughly 12 liters of water to grow literally one almond. But this pattern of water intensive production being done in a water scarce place only to then be exported abroad is not just isolated to California. So for number two, let's go to India, and we focus on these northwest regions in deep red. And on the right, I'm putting up the pattern of land use for arable land in those regions. And we want to see two things. First, how intensively this land is used for agriculture in general. So roughly 95% being actually planted and only 5% left fallow. And of the fraction that's planted, about 50% is going to wheat and rice, relatively water intensive staples. And just as a comparison, the typical hectare of arable land in the sample we're going to have looks more like 2/3 being left fallow. So that extensive margin, much less used for agriculture. And even within the fraction used for agriculture, much less used for rice and wheat. And international trade seems to have a role to play here too, in that India is now the world's leading exporter of rice. And so it's examples like these that have led scientists and policymakers to draw the connection from global agricultural trade to global groundwater depletion, or in general, overuse of our freshwater resources. And so to quote from Rosa, what they sort of summarize their findings with: the globalization of water through trade contributes to running rivers dry, an environmental externality commonly overlooked by trade policies. And so then it's usually a short walk to go from trade drives overuse of resources to trade may in fact be bad for welfare. At least that is sort of the common story. And so what we want to do in this paper, if you want to put it simply, is simply ask, are they right? Are they thinking about this problem correctly? Or is there more nuance to be had? And so more precisely, what we're going to ask is, how do global agricultural trade patterns and policies affect long-run water availability, agricultural production, and welfare, both across space and over time? Now, for any folks in the audience who are trade economists, you're probably thinking Dixit and Norman, various neoclassical trade theories, screaming at me about the gains from trade. Let me tell you specifically what we're going to do and what we're going to find before you come shout at me. So what we're going to do first, we're going to proceed in 4 steps. We're going to first compile a globally comprehensive geospatial data set on water and agriculture. So to the best of our abilities, we're going to try to give you a complete picture of where water is available, how it gets used, what crops get grown where, and what crops get traded where. Then with that data set in hand, we're going to establish a series of facts about the allocation of water in global agricultural production. And the first 2 facts, which I'll group together for today, is simply that there's vast heterogeneity, both in the pattern of water availability and in the pattern of water use across space. And so for that pattern of water availability, we're going to mean that both in a stock sense, so current water table depths, but also in a flow sense, thinking through rainfall or other types of freshwater recharge. And then for use, what we're going to show is that agriculture is far and away the dominant consumptive user of water, with over 90% of consumptive water use going into agricultural production as an input. And so what we're going to see for that heterogeneity in water use is that it primarily follows patterns of agricultural production. And then even though we're never going to directly talk about trade in water, there is going to be a very real sense in which water is being reallocated across the globe, but through a factor content sense in agricultural trade. So there's going to be some water content embedded in the wheat and rice that gets traded abroad. And through that, water is being sort of reallocated across space. But then the second set of facts that we're going to show, facts 3 and 4, is that on either side of these agricultural markets, there are pervasive distortions across space. First, on the input side, what we're going to document is that most places in the world, fresh water is extracted under open access regimes, which means there's not going to be a price for water, nor are there tradable property rights for water. Instead, if you have land that is close to some freshwater source, it simply just means that you need to go pump the water, but it is sort of free for the taking. On the output side, we're going to have the vast array of taxes, subsidies, and tariffs that countries impose on agricultural production. And so there are going to be distortions on both sides of the market. And so in some sense, we're going to be in a world of second best, where it's possible that, number one, those distortions could lead to losses from trade. And I'm going to show you that or sort of underline that a bit more in a second. But at the same time, the distortions could potentially be canceling each other out. And so part of what we're going to want to do when we get to our quantitative exercises is think about sort of the relative strengths and balancing of both sides of the market distortions. And then what we're going to find in fact 5, which somewhat surprised us, but maybe doesn't surprise you, depending on what your priors are, is that despite the fact that we have these sort of pervasive distortions on both sides of the market, the general pattern that we find for production is that water intensive crops do in fact seem to concentrate most in water abundant locations. So in contrast to almonds in California, a very water intensive crop being grown in a place that's very water scarce, the global pattern is much more of what you would have expected from standard Heckscher-Ohlin type trade theory, where the places that have a lot of the resource are the places that do that resource intensive production. Nevertheless, we find some places that do this water intensive production unsustainably. And those are going to be kind of our California and India examples, but I'll take you through that when we get to the facts. With these facts in hand, we're going to calibrate and write down a quantitative dynamic spatial equilibrium model for world agriculture, where we're going to include both the intensive and extensive margins of agriculture, like that India example. We're going to have both Ricardian and Heckscher-Ohlin motives for trade. So countries may trade because they are the more abundant in a particular resource, like arable land or water, but also because they may be more or less productive at growing particular types of crops. That's that Ricardian motive. And everywhere in the world, periods of agricultural production are going to be tied together through regional water budget models. So what that's going to mean is that water today is going to determine where it is best to grow particular crops today. And at the same time, depending on where I grow crops today, that is going to determine how much water is left in a particular location for tomorrow. But this is where those distortions come in on both sides of the market, where you have that open access externality on the input side, which is governing the sort of cost or, in explicitly lack thereof for attaining water in different locations. And then on the output side, you have those agricultural policies, which are shifting around where it is best to do particular types of agricultural production and trade. And so with this setup, we're going to be embedding kind of a classic mechanism from a simple 2-country model from Brander and Taylor in the late 90s, where they show that with open access, trade can in fact lead to losses in this kind of environment, where you have this open access distortion on the input side. But agricultural policies on the output side, in the second best sense, could potentially sort of cancel out those losses and still lead you to the classic result that gets gains from trade. But if you were thinking Dixit and Norman, Levi, there's obviously gains from trade, this is sort of the mechanisms that suggest that in this environment, it is possible that we could end up having losses. And then finally, what are we going to do once we've built this big machine is we're going to use it to characterize trade and welfare outcomes. So we're going to do a standard autarky counterfactual where we shut down all international trade in agriculture. That's going to allow us to adjudicate whether or not there really are gains from trade and for whom. both in the transition and sort of in the medium run where we project out 30 years. And then to get at that second best sort of margin, we're going to also do some counterfactuals that I likely won't have time to show today, where we sort of move around those output side distortions for the taxes, tariffs, and subsidies on agriculture and ask whether the existing ones exacerbate or mitigate regional water depletion. Okay, so that's the plan. What are we going to find? So we're going to have three main results. First, a global pattern. Second, sort of regional pattern. And third, something about those relative gains and losses. So that first global pattern, what we're going to find is that global agricultural trade dramatically reduces how much land and water gets used in agricultural production. So another way to say this is when we go to autarky, global land use is going to nearly double. Global water use is going to go up roughly 60%. And so trade is actually playing the role of preventing water depletion over time in most places in the world, and that's going to lead in most places to welfare gains in the long run. So, immediate pushback on the conclusion of the scientists and policymakers that we started with. To kind of break down those patterns across space, our second main finding is going to be that it's in particular those most water scarce regions that are benefiting the most from trade, and we think this is pretty intuitive. Places like Saudi Arabia, who in principle are currently importing a lot of their food from abroad, so most of the water intensive production they import, and now in a world without trade, you need to try to grow wheat and rice in the desert, and that's obviously very hard, and so you end up depleting the limited groundwater stocks that you have. So those are the places that benefit the most from trade, places that had very little water to begin with. Nevertheless, there's a little bit of nuance still to be had. And so our third main finding is that liberalizing trade, and you can think about this both through the autarky counterfactual, but also through our second best counterfactuals, can be harmful for specific regions in specific contexts. And so what we find when we do the autarky counterfactual is that California and India both actually do avoid extreme depletion under autarky. So shutting down their access to international export markets does save quite a bit of water for those two places. And then when we do our second best counterfactual, one of the ones that we do is we reverse the historic Uruguay round of trade liberalizations. We find that sort of series of GATT and WTO negotiations actually led to increased water depletion and lower welfare. And so because you're in this world of distortions on both sides of the market, the welfare predictions can be somewhat nuanced both across space and across scenarios. Okay, so that's where we're going. Let me just give you a taste of the literature, mostly just to say that there's been a lot of work on trade and the environment, but mostly focused on carbon externalities. There's been very little work on how natural resources come into the picture. As of late, Fareed Faroqi and co-authors have a very nice paper on deforestation. We are, tackling water instead. As I previewed before, if we jump down to that fourth bullet, there is a literature thinking about simple two-country or small open economy models where they're trying to understand this mechanism of what happens to the gains from trade when one of the inputs into the tradable good is extracted under open access, and they show that you can have these long-run welfare losses. And so part of how you could interpret what we're doing is doing a quantitative evaluation of whether or not that mechanism has much bite. And the closest model we're building off of is from Arnaud, David, and Corey's paper. We're bringing in all the dynamics and all the water. Okay, so let's get into the facts. So we're going to have a lot of hopefully pretty maps, and that's how we're going to walk through this. And so I'm going to do this through the lens of a water budget model, which is going to end up being embedded in the quantitative model that we take to the data later. And so I want you to think about this as for particular regions in the world that we're going to call Q. So we're going to think about these as aquifers. So if you know anything about the US and water, go ahead and think about this as the Ogallala Aquifer or the Central Valley Aquifer in California. And the water budget is essentially starting from some initial level of wealth. And for us, that's going to be water table depth. So depth Q0 around the year 2003, that's our time zero. This is your initial stock, what you have in your bank account of water, so to speak. And then your water budget evolves according to how you consume from your stock relative to how much income you get in the form of recharge, which is mostly rainfall, but also runoff from different regions. Okay, so we're going to walk through this piece by piece. And so the first component I'm showing you is that initial stock around the year 2003 of water table depths. So red means the water table depth is very far from the surface, so water is not very abundant. Blue means you're very close to the surface. It's very easy to pump water to the surface to irrigate your agriculture. And so we see if we focus on the US, very red in the US West and Southwest in particular, very blue in sort of the breadbasket of the US in the Midwest. Okay, so you can think about that as sort of our measure of initial wealth. Now, before I break down consumption and recharge, let's look at sort of the overall sort of net savings or net spending from that budget. And we're going to use GRACE data, which comes from the NASA, that's showing us how total water storage is changing all across the world. And so red here are places that are losing water most rapidly. Deep blue are places here that are gaining water most rapidly. And if you zoom in on India, that's the map I showed you in that second example. And so to put some of these numbers in context here, we have roughly a range of minus 200 cubic meters per hectare to plus 200 cubic meters per hectare. For context, rice takes roughly 6,800 cubic meters per hectare to grow. And so these are relatively small trends. We also can say here that roughly 50% of these grid cells are gaining water, roughly 50% are losing. You might think that that's tautological. There's two reasons why it's not. Number one, we're only restricting here to arable land for all of these maps. And so it's possible that you could be losing or gaining water on arable land relative to non-arable, but it's also possible that we're losing fresh water to the oceans as well. So that it's not necessarily true that these things should cancel each other out. Nevertheless, it does look like a mostly balanced picture with relatively small trends. Okay. The second type of heterogeneity in water availability then, so we already saw that initial heterogeneity in wealth. Now what about that heterogeneity in income? Now we're plotting the main component of recharge, which is rainfall. Places that are deep blue here are places that get the most rainfall. Places that are kind of this palish green yellow are places that get the least. Places that are grayed out are where there's no arable land anyway. And for context as well, so these deep blue regions are places that if I tried to grow rice on the entirety of my arable land, I would still have water left over that I would be gaining in depth. So I don't need to dip into my groundwater resource stocks to cover that full acreage in rice. On the other hand, of course, as I get closer to zero, the only way that I could be growing anything is if I draw down on my water stocks. And so you see that kind of mostly in the US West and Southwest. Okay. Now for the heterogeneity in consumption. So here what I'm doing is I'm plotting a measure called the water footprint. And so that's cubic meters of water use per hectare. And I want you to mostly focus for now, just look at the US for a second. And I want you to think about where the population centers in the US are versus what the spatial distribution of this water footprint measure looks like. And I think you can very quickly identify that New York City is not showing up particularly big on here. What's showing up are places where intensive agricultural production is being done. So if you zoom in on California, you just see this strip along the Central Valley that's this dark blue and green, or most of the US Midwest. And so that's precisely because agriculture is far and away the dominant consumptive user of water. And so our stylized fact here is that roughly 90% of global water consumption is actually used as an input into agricultural production. Roughly about 4% is used for households and another 4 or 5% for industrial use. Far and away, it's agriculture that plays a big role. And that's why we're going to do a model of agriculture. But you also see here the vast heterogeneity in this pattern of use as well. All right. And now part of that agricultural consumptive use of water gets embedded in international trade. And so roughly 20 to 25% of that consumptive use gets shipped abroad through the trade and agricultural production. The US is one of the largest net virtual water exporters. And at least in the 2009 to 2011, which is the era of data that we are focused on, China had moved into sort of the lead as the world's largest net virtual water importer. Great. Okay, so that gives us our patterns of vast heterogeneity in water availability and water use, and how much of this water is being shipped around the globe through international trade. Now let's zoom in on these distortions that are also very heterogeneous across the globe. First, on the input side. So what we're doing here is documenting places around the world where we can find evidence of active formal water markets. So places in which there is documented trade in property rights over either surface or groundwater. In light blue, we're coloring places where uh, there were once active markets, but at least seem to no longer be active markets, or there are informal water markets where there's some kind of trade happening, but not sort of in a formalized sense. And then gray places are places where we see no evidence of tradable water rights. And so if you just remove from our sample these places in dark blue, places where we can find concrete evidence of active formal water markets, so think Eastern Australia or the Western US or Chile and Spain. If I remove all of those countries, I still find that I cover more than 93% of global agricultural production just in places that have no formal water markets. And if you know anything about the California situation, us coloring it dark blue, just as an example, is maybe a generous thing on our end. So we think this estimate is conservative because in California's case, we're only thinking about governing surface water use. It's very hard to monitor groundwater use. And so in principle, these formal water markets might be very partial in their coverage anyway. And so this is why we think those input side distortions, this open access regime is a useful one to be thinking about when we get to the quantitative model. Then as well, we have these distortions on the output side of the market. And here what I'm plotting are measures from the World Bank called nominal rates of assistance. And these are, you should think about simply as a wedge between the price that the producer gets at the farm gate versus the price they would get in an undistorted world market. And so positive numbers here are places that are getting net subsidies to agricultural production. Negative numbers here, the red, are places that are getting net taxes on their agricultural production. So you also see a lot of heterogeneity across the world in these numbers, both in terms of magnitude, but also just in terms of sign. And usually it's the richer countries who are on net subsidizing, and oftentimes low and middle income countries that are on net taxing. Okay, so we have the vast heterogeneity, both in patterns and use, or patterns of availability and use of water, but also in these distortions. Nevertheless, what we find in fact 5 is that water intensive crops tend to locate primarily in water abundant regions. And so the way we're going to see this is we're going to construct this kind of water footprint measure that we mapped before, where we were thinking about cubic meters of water per hectare, where we're using data on cropped area fractions around the world, and measures of water intensity per hectare for those crops from agronomic models. And what we're doing here now on the left is a bivariate map of this water intensity measure of agricultural production versus different measures of water abundance. So this is in some sense fact 2 versus fact 1 plotted against each other. Okay, and so what I want you to focus on is how much of this graph has colors that are focused along the diagonal from that deep gray to that light pale yellow. These are places that if they get a lot of rainfall, they do a lot of water intensive production, or if they don't get a lot of rainfall, they don't do a lot of water intensive production. And we can summarize that a bit more concretely in these decile plots. So on the x-axis on the right, I'm plotting deciles of rainfall where we get more rain as you go to the right. And on the y-axis, I'm plotting this water intensity of arable land measure. And you see this pretty neat upward sloping line. It suggests in places that get a lot of rainfall, they do mostly water intensive production. Okay, we can do the same thing for groundwater access. So now we're plotting against higher water tables, so closer to the surface. And you see the same kind of strong correlation that places that have a lot of water abundance in this stock sense versus the flow sense on the right do a lot of this water intensive production. But if I go to instead, our deciles of water change. So these are places that are gaining versus losing water most rapidly, where you're gaining water most as you go to the right. If you start on the right, you see places that are gaining water. Generally, these are places that get a lot of rainfall. And so they can sustain very high water intensity of production. But if you go all the way to the left, you have this dot up near the top that says there are some places that are losing water most rapidly. And so this is that Northwest India type of example that are also doing a lot of water intensive production. And so it suggests that water intensive production is sometimes happening in places that cannot sustain it in the long run. And so to summarize everything we've gotten through in the facts to this point, what we're plotting here on the x-axis now is groups based on being in the bottom quartile of different measures of water availability. And so all the way on the left, you have places that are not water stressed by any metric. They have top 3 quartiles of rainfall, groundwater availability, and changes in total water use. And by far, those are the places that do the most water intensive production, kind of as you would expect. But if you go to the second to last one on the right, these are places that have bottom quartile groundwater table depths and are also losing water quite rapidly. And that's the second most water intensive bucket that we have. So for the most part, water intensive production being done in water abundant places, but sometimes in places that don't seem like they will be able to sustain it. And so these are the patterns that we want to try to understand through the lens of the model, and then take that to how does this sort of make sense of who gains and who loses from trade. Okay, so let's go ahead and jump into the model. So the way this model is going to work, the fundamental sort of geographic unit is going to be what we call a field. We're going to index that by F. Every field is going to be tied to some country I and also tied to some particular aquifer Q. So this field can be in California's Central Valley, so it's in the US, and it's tied to the Central Valley's aquifer. Time here is discrete, and each of these fields is going to be then further split into a continuum of parcels, and this is going to allow us to do the usual discrete choice sorts of things that we all enjoy doing. Okay, then I'm going to have 2 sectors in this model. The first is just going to be a homogeneous outside good. So this is going to be everything that's essentially not agriculture, any kind of manufacturing or tradable services. And I'm going to keep that sector pretty simple. So freely traded, homogeneous, that's going to be our numeraire. The second sector is going to be agriculture. We're going to have K different crops, and those are all going to be distinguished by the identity of their exporter J, and all of these things are going to be traded. So that side of the model is going to be as vanilla as we could possibly make it. So we're going to have non-homothetic preferences where you spend your first, X dollars on agriculture, the rest goes to the outside good. Within that bundle of expenditure on agriculture, it's just nested CES over different varieties of crops. And then within wheat versus rice, you have Brazilian wheat versus American wheat with the elasticity of substitution sigma for that. Ag prices are going to be subject to iceberg costs as usual, and then as well these policy distortions that are going to map to those nominal rates of assistance I mapped for you earlier. Okay, the model is going to be populated by laborers who are assigned to these parcels omega. So they dot the map, and each laborer is going to be making discrete choices. First over, do I farm or do I work in the outside sector for a wage? And if I choose to farm my parcel, which crop do I choose to grow? And that's where the discrete choice is going to happen. And all of these laborers are going to take as a fact of their problem that the water that they need for agricultural production, should they choose to do it, needs to be drawn from the aquifer that is pertinent to their field. And that aquifer, the water in it, is going to be treated as an open access renewable resource. So I'm not going to some market and paying a price for water. There's simply going to be some physical cost of pumping or acquiring the water, but I'm not paying for anybody's property rights over it. Okay, so how does that agricultural production happen? So consider you are the farmer on some parcel omega on field F, that's in some country I, aquifer Q. You're going to be endowed with 1 unit of labor for yourself and 1 unit of land. That's just a normalization of units. And then you need to acquire some groundwater as an input. And with those endowments, you are going to use a technology that is Cobb-Douglas over labor and some bundle, what I'll call natural capital. And that natural capital is going to be a Leontief combination of the land that you have and then groundwater. And phi k here is going to be playing the role of how much water per unit of land do I need to grow a particular crop. And so rice is more water intensive than barley. And so phi K is going to be higher when K is rice than it is when K is barley. Okay, and then on every parcel, you have an idiosyncratic draw of productivity, AFK, that's drawn from a Frechet distribution where the mean is given on the right there by AFK. Okay, now the missing piece here is how do I get that groundwater? And the way we're going to do it uh, right now is a farmer is essentially going to take part of his labor. Some of it goes into actually cultivating the crop in that previous technology, and the rest of it needs to go to actually pumping or operating the pump to get the groundwater. And so groundwater, the technology there is just linear in how much labor you use for pumping, and the productivity of that labor is going to depend on the identity of the aquifer, but most importantly, on the current water table depth of that aquifer. And so the idea there is if water is close to the surface, then I don't need to spend much labor trying to pump to get any water. On the other hand, if groundwater is very far from the surface, then it's going to require more labor to get any water for my crops. Okay. And this upsilon Q, this kind of fountain looking thing, which we've chosen precisely because it looks like pumping water out of the ground, is in the background, soaking up a lot of the heterogeneity across space that could come from variation in levels of rainfall that we're not perfectly capturing, or variation in surface water, or pumping technologies, or all those sorts of things. And so when we estimate the model, this is going to be a structural residual that we try to back out to match those trends in water availability. And so it's going to be soaking up a lot of this sort of extra heterogeneity. Okay, and so that's essentially the setup for the model. Everything else is kept deliberately simple. And so what this is going to mean is that when I put these two pieces together, when the farmer optimizes over how do I allocate my labor between actually cultivating and pumping groundwater, I'm going to be able to write my production function in the following way. It's going to look like my idiosyncratic productivity, AFK, omega, times this thing M, which I want you to think about as a yield gap. So AFK is my maximum potential yield that I could get if I grow crop K on my parcel omega. M is going to be a number between 0 and 1. That is the percentage sort of loss on my potential yield that I am going to get. And that loss is bigger, so M is closer to 0, if phi K is high, so that means I need a lot of water to grow a particular type of crop, or if the depth is large, which means I need to pump from very deep to get any water. And so this is the way in which water scarcity is going to affect patterns of production, because it's going to essentially be more expensive in the sense of lost yields if you're trying to grow water intensive product, high phi K, in a place that has low water availability, which is a large D. Okay. And then we also still have the heterogeneity in the Ricardian sense coming through that heterogeneity in potential yields, those AFK. All right, so then what does an equilibrium look like here? An equilibrium here is given some set of policies and given some set of initial water table depths. An equilibrium is a whole path of consumption, output, prices, cropped area shares, water table depths, and water extractions, such that everybody's maximizing their utility. All those laborers are doing sort of the best discrete choices they can to maximize their returns. So some of them are going to go work in the outside sector. Some of them are going to choose a crop that maximizes their revenue. And what I'm doing here is putting up for you the expression for cropped area fractions on field F for particular crop K in some period T. So this is what fraction of that particular field in the Central Valley is used for growing wheat, let's say. And that fraction is going to be higher if, as you go term by term through the numerator, if the price that the farmer gets at the gate, inclusive of distortions, is relatively high. So if tau times P for wheat in that field is high, if the potential yields are high, so that's a high AFK, or if the yield gap is small, which means M is relatively close to 1. Then the share of the overall field that goes to crops at all is going to depend on the profitability of all those different types of crops versus the sort of yield that those farmers would get from instead going to work in the outside sector. That's the wage. But then when I pin everything down in the model, that's ultimately simply going to be the productivity that that country has in the outside sector. So if we're relatively good at producing manufacturing versus agriculture, there's going to be a lot of farmers who are leaving their fields fallow, instead working in the outside sector. And so all of these pies are going to be relatively low for any different types of crops. Okay. And then to complete equilibrium, markets need to clear, and then depths need to obey their law of motion. So this is what keeps sort of these spatial equilibria period by period tied together, because how much I extract today for current production, that's X, determines how much or what my water table depth is tomorrow. So that's giving me my change in D. And so this means that although I've written down a model in which no one's making any kind of dynamic choices, precisely because I have this open access externality. So if I'm a farmer, there's no sense in me projecting how my extraction today is going to affect the depth tomorrow, because I'm small relative to the size of my aquifer, and I have no property rights over the water in that aquifer. So I'm not making any dynamic choices, not because you know, not because Levi is imposing that, but because that is what's optimal for that farmer inside the model. Nevertheless, the evolution of depths matters here. And so the dynamics do have some bite, because that pattern of production today determines the depths for tomorrow. Okay. Now, how do we quantify this setup? So let me take you through quickly the data that we have, and then I'll just give you a sketch of what we do, and then we can get to the results. So we're going to have a sample of 52 countries that account for the vast majority of agricultural value and population, 22 crops that span different water intensities, and 205 aquifers that partition arable land in our sample. We have a bunch of data that comes at the field level from different agronomic sources. So we get these potential yields, these AFKs from GAIAs, and crucially, we have those potential yields even for crops that in the data we never observed being grown in a particular place. So I never observed bananas being grown in Minnesota, but GAIAs is giving me some estimate of what the potential yields would be for growing bananas in Minnesota. Then from EarthStat, we get at the 5 arc minute level data on these cropped area shares, these pi FKs, so I can observe what fraction of a particular field is being used to grow wheat versus rice. And we were using that to get those maps in the fact section earlier. Then at the country level, we have a bunch of standard data from the FAO and the World Bank on output, prices, distortions, and harvested area. From Comtrade, we have the trade flows that we're going to exactly match. And then at the aquifer level, we have those data sets that we saw in facts 1 and 2 for sort of an initial level of depths. That's from Fanli and Miguez Macho. And note that for that, we can start out of steady state. So we're matching roughly the cross section around 2003. And then Grace, this data from NASA, is giving us changes in total water storage from 2003 to 2016 that our estimation strategy is going to try to exactly rationalize. Okay, and so we have a huge set of parameters that still need to be calibrated or estimated, despite the fact that in the data, we have a bunch of things that were directly observable. So I'm not estimating the potential yields because I'm just grabbing them straight from GAIAs. But we still have a lot to estimate. We're going to do it kind of in 3 steps. So we have our demand parameters at the top there, our production parameters in the middle, and our hydrology parameters at the bottom. A lot of the hydrology parameters and some of the agricultural production parameters, we're just going to calibrate to the literature or direct things we can observe in the data. So for example, those crop-specific water intensities, we're going to be taking those from a paper in the hydrology literature that's directly trying to estimate how much water does wheat need per unit of land. And so we're going to directly bring that kind of thing in. On the demand side, we're going to do something very standard for trade folks, because our model is going to admit a gravity regression specification. And so I'm just directly going to match the trade flows that I see in the data and back out the demand shifters and trade costs that exactly rationalize those flows. So I'm matching my demand side exactly. And on the output side, what's left is that technological heterogeneity, theta, which is governing the dispersion in my Fréchet shocks that gives me my discrete choice. Those mean labor productivities in the outside sector that determines how much arable land I actually use versus how much I leave fallows for folks to work in the outside sector. And then those upsilon Qs, which determine how efficient am I at pumping. And so I'm going to match targets both in land use and water use that I build up from those pies, those earth stat cropped area shares. And I'm going to be able to match land use perfectly. And I undershoot in a few regions that have very high rainfall in Southeast Asia for water use, but we get the pattern bang on. Okay. And so for the set of counterfactuals that we're going to do, given the time, I'm only planning to show you the autarky counterfactual. So that's number one. When we eliminate all trade in agriculture, which just means I set my trade cost to infinity, that's going to allow me to answer the question whether or not existing trade in agriculture improves or worsens the allocation. And then our second and third counterfactuals, which I'll point you to the paper, are thinking about from a current set of trade policies on the output side, what if I further liberalize, or what if I reverse liberalizations that have happened in the past? Okay. So let me take you through what happens when we shut down trade. I'm going to do global patterns, then regional, and then I'll basically be done. And so the first thing that comes out right away is when I move to an equilibrium where I have no trade, the amount of arable land that I need to put into agricultural production nearly or basically doubles. And so we see very little variation over time as the depths continue to evolve. Most of this happens right away upon reallocation. I need to recruit a bunch more arable land into production now that I can no longer import crops from abroad. I see the same thing for water extraction, but what I want you to notice, if we go to the left, this is that initial change upon reallocation when I shut down trade, is that global water extraction only jumps by about 55% relative to global cropped land, which basically goes up by double. And so that means part of the adaptation that happens is that when I recruit more land into agricultural production, I also shift toward less water intensive crops. So on net, we are shifting toward crops like barley and away from crops like rice when we have to when we shut down trade and have to do more of this water intensive production ourselves. Okay, and so what this means is that I end up in a world where global average aquifer depth starts to decline pretty rapidly. So we're only going about 30 years out in these projections. And what you see in the baseline, consistent with those trends from Grace, is that global average aquifer depth wasn't really moving much in the baseline equilibrium because those changes in total water storage were relatively small. But when I shut down trade, the only way that I can sustain the kind of agricultural production I need to do involves using a lot of groundwater, and that over time is drawing down my aquifer depths on average all around the world from roughly 18 meters below the surface to about 30, only 30 years out. Okay, and so what does that mean for welfare, sort of in this global sense still? What we see is that agricultural productivity falls, and so global average yields drop about 44% in that initial autarky reallocation. And the key thing to notice there is that because the depths themselves don't immediately change when I shut down trade, those are some stock or state variable that are kind of fixed. This drop in yields of 44% is entirely through a worse spatial allocation of production. I'm recruiting less productive land into production, and that's what's dropping my yields so much. When those yields drop, agricultural prices rise. So the food CPI increases about 15x in that initial autarky reallocation, with modest further increases each year thereafter. And non-agricultural production falls by about 16% because I'm recruiting more land into agriculture and therefore more labor into agriculture and therefore less going to that outside sector. And so although I'm not going to give you, one summary welfare number here, in a revision of the paper, we're going to have that for you. But in the numbers we have right now, the relative size of the sectors isn't quite bang on in the data. But we can still sign the welfare effect here because I can see that agricultural production, which is going to give me my C of the outside good, is going to drop. But the food CPI, that PIT far on the right, is going to go up. And so both of those things are going to lead in general to welfare drops. And so we know that for most places in the world, when I shut down trade, welfare is going to fall. Now, how does that look across the world? And I'll start to wrap up. So we see that allowing trade is preventing extreme regional depletion. So places here, this is the baseline. But when I go to autarky, this is on the same scale. You see how many more regions go from moderate colors to this deep red, places that lose water quite rapidly when I shut down trade. And this is mostly for places that are in this lowest quartile of depth and precipitation. So places that already didn't have much water. When I shut down trade, they see these huge negative changes in their water trends. And so Turkey, for example, a place that was a big food importer in the baseline, sees drastic movements in its median depth in its aquifers as you go to autarky. But there is a little bit of nuance, and this is where I'll wrap up. And what I want you to do in this map is just zoom in on California Central Valley for a second. And so that is a light green area, which is a place that if I'm taking this ratio of autarky extraction to baseline extraction, it actually extracts less in autarky than it does in baseline. And so median groundwater depth actually declines less rapidly in autarky than in the baseline in California Central Valley. And to the extent that groundwater depth ends up acting a bit like a sufficient statistic for welfare through the lens of this model, that suggests that welfare in California Central Valley actually may be a bit higher without trade than it is with trade. Given the time, I'll go ahead and wrap up there. Uh, Thank you guys for having me. Looking forward to a lot of questions.
That was great. Really, really fascinating. We've got a couple of questions in the Q&A. I just had a minor one, which was
Mhm.
on like the dynamics of this is super fascinating. Is there any sense that you get to a point in some of these places where extraction just collapses? There's like a tipping point where you can't get any more water out, or is it just a smooth decline that costs are increasing all the time, but nothing?
So, there's an answer that we think probably applies to the real world, and then there's an answer through the lens of the model. Through the
Mm,
lens of the model, we are constrained somewhat by the assumptions that the hydrological literature makes, given the data we're bringing in. And the general assumption there is that these are kind of infinite bathtubs. So all that matters is how deep do I need to go to get the
right.
first water, but there's no sense in which we have a good estimate of where the bottom is. Um, but you're totally right that a lot of these aquifers aren't this unconfined object. There are many aquifers that are confined, so you would hit a bottom, and then the cost would just skyrocket because there's no way to get any
I
water.
see.
That's part of why we're cautious with our projections, and we only go 30 years out. Uh, Another reason why we're cautious about that is because you'd also think that different types of adaptation may come into play as you enter this kind of day zero where water gets so expensive to extract, where countries might start, trying to find ways to solve the property rights problem, which we're kind of punting on here.
Awesome. Well, let me ask some of these questions. So,
Mhm.
two-parter from Juan Pablo Martinez. Do you
Mhm.
think that introducing capital into this model would change your results? And can you comment on the role of other products that are also water intensive, like mining and metals production?
Sure. Let me take the second one first, and then I'll get back to capital. So when it comes to mining or any other type of water and intensive production that's outside of agriculture, it's helpful to distinguish between two things. There's water withdrawals, and then there's consumptive water use. That 90% number I gave you for agriculture before is consumptive water use. That is when I use the water as an input into this type of production, it then gets lost to the local environment. A lot of types of production like mining or to stick with the news, data centers that use a lot of water, a lot of that water ends up getting treated after it's used in that kind of production and recycled into the local system. And so for our purposes, what's important is that consumptive water use that leaves the local area. If you're simply sending the water through the mining production and then it gets treated to get out the pollutants and then sent back into local rivers and streams, then that's we're not capturing that, but we also think it's not subject to the forces that we're interested in studying. So that's why we leave it out. Um, as far as bringing in capital, yeah, so I think we are doing kind of a simple thing here where the farmer simply has his labor to allocate between pumping and agriculture. If you could bring in capital to the agricultural production, I don't think that really changes much of anything. You might think about instead bringing in electricity in particular into the pumping technology, which is kind of the standard thing to do. Uh, my hunch is that it doesn't change our results much, but we are working through a revision of the model right now where we're writing down something that is at least much more amenable to answering your question more precisely, so that I don't just have to rely on a hunch. So I guess I'll just ask you to wait until the next version of the paper comes out, which is hopefully soon.
Good. And a couple from Kavitha. I'll ask one. Since there's no distinct factor market for water, does that mean we would be unable to simulate water policy instruments directly, or more broadly, how do you think about this missing markets problem?
Yeah, that's great. So yeah, in the model as it's written down right now, I don't have any way with the the margins that are currently in there to simulate a policy that looks like the US is going to start charging everybody for water. That's not set up in there. There is a really nice recent paper from Brander and Taylor, where they take their kind of simple two-country model and they show how to endogenize property rights in that kind of setup. And so we are thinking about in this revision trying to bring in ways that would allow you to at least simulate the kind of things that would happen if you were able to, institute at least some kind of water market. I think what you would want to do is go all the way to the far extreme, which is what if I had a global planner who could simply solve all of these input side distortions? I think at least we've been pushed on that kind of thing in the past, which would be what would happen if you actually had perfect water markets everywhere in the world. And that turns out to be a very hard problem to solve in this setup, specifically because you have 200 different state variables, which is the current water table depths all across the world. And so if you try to do sort of the first best thing where one planner is having everybody optimally use water. You're trying to govern a trade model with 200 state variables period by period, and you're solving the full dynamics. And that we don't think is impossible, but it has been beyond what we were going to do in this paper. Yeah, it's tricky.
Right. And then one from Heidi. Yeah, what factors or conditions allows for agricultural autarky to be beneficial and not harmful? So maybe just give some more color around like the intuition of when trade is helping and when trade is hurting.
Yeah, perfect. So this is a lot of what we're doing in the revision right now. So first, why trade is we think still helping. So I think the Ricardian forces here are actually doing a lot of the heavy lifting. And so you have to remember that part of the gains from trade here are coming from the fact that I can get my wheat not simply from a place that has more water to grow wheat, but from a place that is better at producing wheat regardless of the water availability. And so part of what happens when I lose access to trade is I lose access to those better wheat producers in that sense. And so we've done a counterfactual that's not yet in the paper where we equalize those potential yields all across space. And you do see, a much different picture of global trade and therefore the welfare gains and losses from trade if I shut down those Ricardian forces. Now, to the specific question you asked on what's determining um, why some countries still, do better under autarky. So the Brander and Taylor mechanism that we think we're embedding here is basically that if I am relatively good at producing the resource intensive goods, so let's think I am California, I am very good at producing almonds, then what happens is when I'm open to trade, I have a lot of global demand for those almonds. I ramp up my almond production. As I ramp up my almond production, I'm lowering my water table depths because I'm using a lot of water each period or more than I would have without trade. As I lower my water table depths, though, I become less productive at producing almonds. And so that shows up through that yield gap that we have in the model as the depth is getting deeper. Even if I have relatively high potential yields for almonds to begin with, I'm losing some of those productivity, some of that productivity over time. Um, and so that's essentially why you can get losses from trade is because I'm always just as good at producing the outside good as I ever was before. But as I export more and more of the water intensive good, my depths are dropping. That's making me less and less productive. So my PPF is essentially shifting in, and I have no way to kind of correct for that. So when I shut down trade, if I'm the Central Valley in California, I'm basically stopping that process of shifting my PPF in by as much as I would have if I was exporting a lot. And so that's what's giving me at least less, or in this case, gains still from being in autarky. Yeah, so in some sense, really what we're doing is you're trading off this PPF rotating in type of force from the open access externality versus losing access to the Ricardian trade partners that you had before. And it's the balancing act of those two things that seem to determine most who gains and who loses.
Great. Caroline's got her hand up. Caroline, do you want to
Mhm.
unmute yourself and go?
Yes, okay. So first of all, thank you. Thanks
Mhm.
very much for the presentation, and it's really impressive work. So I think that I have a very related question, actually, to the last question. So am I right in understanding that trade is mostly beneficial in your model, not because the water externality disappears, but because you have like physical scarcity, and that is partly internalized through the extraction costs? And is this kind of then the main mechanism that is driving the results, or is it also shaped by other, like, I don't know, calibration or the existing like geography of agriculture policy distortions? And yeah, and also maybe like if you could say something a bit about the policy implication of this, then that would also be very interesting.
Yeah. Okay. Um, So I think you're spot on with the first part of that question, where that was also our hypothesis. It seems that the way we used to frame it before is that nature was somewhat replacing the market in the sense that as water tables got lower, the cost of pumping was still getting higher. So even though you weren't paying for water, you were still internalizing some of the scarcity. We thought that was a lot of what was behind our fact five patterns that we showed you before the model two. But now we've done some new counterfactuals that I wasn't able to show today, where we shut down that force, where nature no longer is substituting for the market, and the scarcity of water table depths aren't affecting those yield gaps. And we actually don't find as much change as we would have expected. And so keep in mind that that mechanism is also already there in some of those, the toy model from Brander and Taylor. Uh, and so you could still have losses even in a world where nature is substituting for the market. But instead, what seems to have the most bite is these Ricardian forces. And so, to some extent, yes, the calibration is playing a big role, but we feel pretty comfortable with this because that is a parameter that we're bringing straight from the Gaia's data. So I'm not doing that as like a structural residual from the model. That is instead based on what agronomic models tell us are the places that are best for growing wheat versus rice. When I shut down that heterogeneity, which there's a ton of, that is what gives us a lot of shifts in the baseline and therefore also in the autarky patterns of production and therefore gains and losses from trade. And then for the last part of your question on sort of policy stuff, so I think we do some counterfactuals currently in here about changing those output side policies. I think, of course, the best thing to do would be, can you get to the first pass where you solve the input side distortion? Then you wouldn't even need distortions on the output side. You would be best if you zeroed those out. Now you're at first best. But in a world where it seems very difficult, at the very least, to solve those input side distortions, partly because of a technological issue of it's hard to monitor groundwater pumping, but partly also it just seems that countries have a hard time setting up these water markets. The output side distortions may be your best tool, and so it can be that if you set those output side distortions in a clever way, you are able to essentially cancel out the effect of the input side distortion. So there is a classic theory of the second best, where your optimal output side distortions may be non-zero because you have this input side distortion. To actually solve for what the optimal set of those policies would be is tricky because it also then essentially involves solving this giant, 200 stock uh, uh, dynamic problem, and so that's still hard to do. Um, but we've thought about doing some things that are, say, like country by country, what is your individual optimal set of output side distortions, given that you are trading with a bunch of countries that also have this input side distortion like you do. We don't have it in the paper yet, though. So the overall policy lesson is output side distortions could, in the second best sense, help, even if you can't do the first best thing, which is establishing a water market.
All right. Well, that brings us all the way to time. So thank you so much.
Mhm.
Our next webinar is going to take place on April 13th when Lakshmi Narayanan from London Business School will present his paper, Green Mortgages. Thanks so much to Levi for today, and we'll hope to see you next time.